This is Professor Todd Elliott. Today is May the 4th, 2025, and this is our first lesson in the JFET. So the JFET is called the Junction Field Effect Transistor, which is somewhat similar to, but very different from the MOSFET. Both the JFET and the MOSFETs are what could be classified as a voltage controlled device, whereby you change the gate voltage, and more specifically the gate to source voltage, and you change the current in the drain. So the voltage controls the current. Contrast this to the BJT, which is a current control device. The base current controls the collector current. Nowadays, I would say there's not a lot of reasons to use a JFET in a new design, because the MOSFETs are much more popular and have a host of advantages. But they are still around, and it's a good way, before we learn about MOSFETs, to step into the pool, so to speak, on other transistor types. Okay, so there's two types of JFETs, much like there's two types of BJTs. Got some leftover text. Just get rid of that. Yeah, sorry about that. It's my earlier test video. Now MOSFETs are a totally different animal, but we'll get there eventually. But anyway, so the BJT, it's NP, 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 and the JFET, it's N channel and P channel. So mostly we'll be looking at the N channel. It's really just the difference of how the voltages, polarity, which ones you're going to use. So over here, you see we have the drain, that's one of the terminals. And we have the source, and we have the gate. So the terminals are drain, source, and gate. On the BJT, this is be an analog to the base. This would be analog to the collector, and then this would be the emitter. They mean totally different things, of course, but that may help you. With the N-channel type JFET, we use a positive drain voltage. So these are going to be positive, and then that must mean that the gate voltage here must be negative. If you're using the P channel, those two polarities are simply reversed. So internally here, what we see, okay, sorry if the line is not being straight, okay, is it looks more like this than what the diagram shows. Okay, they're supposed to be symmetrical, but anyway. Okay, then you got your two leads coming up top and bottom, and then this is going to be the gate. So this would be the gate. This would be the drain, and this would be the source. Okay, so what we have here is for the N channel is this conducting channel is doped with free electrons, okay? And then these two P regions here, and again, they're larger than what's shown in this diagram. They're sort of internally connected and brought out to the gate. So by controlling the voltage at the gate, then we can either repel or so push these two regions together to constrict the flow of current, and the main drain current is going to be down like that. Or we can open up this channel to allow more current. So it's kind of like a garden hose. I've always used this illustration with my students. If you constrict the garden hose down, you might be able to stop or greatly reduce the flow of water, but if you let it go, then you have the full water flow. Okay, so if you want to know how a JFET works, just remember a garden hose, and there you go. So the basic circuit looks like this. So we're using a power supply here called VDD. That's supplying our positive bias voltage to our gain. This is for current limit. And then for our gate voltage, we need a negative voltage here. So the N channel, this voltage here is negative, and this voltage here must be positive. Okay. Now the real voltage ultimately that we're interested in is the voltage between the gate and the source, and that's going to be just like that. Okay, this voltage here, the drain to source voltage VDS, that's going to be the voltage between the source and the drain. That's kind of like voltage VCE, collector to emitter voltage, if you're working with BJTs. If I change this over here, I'm just gonna redraw this. Is the schematic symbol, and that line is supposed to be straight. So this would be sort of like the equivalent schematic diagram, just so you can see the schematic diagram and then the internal cutaway, just to help you understand. Okay. That. I just don't like these tablets. Just never can get used to them. On the iPad, it's fine, but this is on the computer, so. Yeah, so anyway, I'll just draw it like that. Okay, and that's going to be negative. And this would be VGG. Okay, and then this would be the actual drain, and this would be the actual source, and then this would be the gate. Okay, so there's the schematic diagram, and there's the cutaway. So this here would be our drain to source voltage, and this voltage here would be our gate to source. Now this is the one we vary this voltage by various means, and that is what is going to ultimately control the drain current by controlling the width of this channel. Okay, hope that makes sense. For the P channel, then the P channel, then this voltage here, we'll do a similar diagram, is going to be negative, and this is going to be positive. Notice how the main channel here is P, and these two regions, and then they're really more kind of like this shape, but that's okay. They're doped in, and they're connected together and then brought out to the gate. Okay, so if we were to do a schematic diagram of that, and then it would look like this, something like this. Okay, so this is going to be negative. This is going to be another arrow coming out like that. If you notice that the gate arrow for the P channel points outwards, and for the N channel points in, just remember it's opposite. It's opposite the base to emitter arrow on the BJT. Got to use all kind of memory aids. As I've said to my students 100 times over the years, I didn't remember this stuff by making it hard. Okay, so in this case, the gate to source voltage would have to be positive, and that would allow us then to vary the drain current. Okay, all right, we got next. Okay, so this is called the drain curve. Okay, so what we're comparing here, and this is very much like the BJT collector curve. So we have VDS here, voltage VDS, and we have current ID. If you were looking at a BJT, that would be IC. Okay, and that BVCE. So the JFETs, they have basically, you don't want to be, this is breakdown, you don't want to be out here, that's destroying the JFET. They have this active linear constant current region. Now JFETs are not, BJTs are absolutely linear if you're up in the active region with a high current gain. JFETs are not, and neither are MOSFETs, by the way. However, they still can act as a constant current source up in the active region here. So that's this green area up in here. This region here, an ohmic region, it can be biased to be a voltage variable resistor. I have some circuits I built with MOSFETs that hopefully when I get some time, I just teach full time and trying to write a book and just do everything. It's just, sometimes it's just impossible, as you know, you all know. But I have some nice circuits I made and tested, and illustrating how to use a MOSFET as a voltage controlled resistor to control fan motor speed. But anyway, it has this also has this region here, but we're not going to worry about that for now. But this region here is saturation, okay, and in the saturated region. Now this where it gets a little tricky. I don't want to get into it right now, but saturation in JFETs, MOSFETs does not mean the same thing at all as in a BJT, which is really gonna mess with your brain. But when we get there, but that's the saturation region. But anyway, so if you look at this little circuit here, so we've taken the gate lead here. This is again an N-channel JFET. Look at the arrow direction, and we tied it to ground. So that forces VGS to be 0. When the gate source voltage is equal to 0, that conduction channel is wide open. Okay, so IED is like at a maximum. And on a data sheet for a JFET, it specifies when VGS is equal to 0, so when the gate to source voltage is equal to 0, which is what we have here, ID is at a maximum current called IDSS, which is like called the saturation current. Okay, so if we basically ground the gate, then this current would be at a maximum. Okay, right? This pinch off voltage, VP, doesn't mean peak, it's pinch off voltage. That's at that intersection. So that is if you set VGS to 0, drain current ID will be at a maximum IDSS, and voltage VDS will be at this pinch off voltage. Okay, so this, and this are all data sheet specs for the JFET, and they all coincide at that point. Okay? All right. Okay, so this here is a JFET which we've commonly used with my students. There's other numbers we've used, but this is one of the ones. And if you just look at the data sheet there, okay, see this IDSS says 0 gate voltage drain current. So this is VGS equals to 0 volts. Okay, it says that the saturation current, IDSS, device to device will be at least 1 milliamp, but it won't be more than 5, and it has an average of 3. So IDSS, it's a highly variable number. Okay, so the device that you have, it could be anywhere in there. So that means the circuit design has to sort of, make that non-critical. Okay, the gate to source cutoff voltage, that's VGS off. Okay, so that is what's the gate to source voltage that will make the drain current equal to 0. Okay, so basically VGS off, okay, right? It sets the drain current equal to 0. Now there is some leakage current, okay, but still, okay. See where it says 10 nanoamps, okay? So this is the cut. So this is the cutoff point, and this is where the JFET acts like an open switch. Okay, so the current is 0. So if VGS equals if VGS 0 causes the drain current to be at a maximum, then increasing the gate to source voltage, which for an N channel means making this voltage negative, at what voltage is required to bring the current down to 0, or how hard do you have to squish the garden hose to make the water flow stop? Okay, device to device, it's going to be anywhere in that range, and each JFET part number has its own upper and lower limits, and every device can fall somewhere within there. So there's a high degree of variability. Okay, this is what's known as the transconductance curve. Sounds really cool, but it's sometimes called just the transfer curve. It's the graphical relationship between the gate to source voltage and the drain current. Okay? So what I said was, right, and I did this in Apple numbers, I believe, but I said, okay, let's assume our JFET part number has an IDSS equal to 12. That's the saturation current. And a VGS off, the cutoff voltage, equal to -7. Well, if the gate to source voltage is equal to 0, then our current here is at a maximum. That's our saturation current. As we increase the gate to source voltage, which for an N-channel JFET means make it more negative. If it's P-channel, you make it positive, but make it more negative. At what point is the current equal to 0? That's the cutoff voltage here. That's right there, and it follows this curve. So you can see the curve is not linear. And MOSFETs have the same curve, by the way. So it's not linear. So when they use this as an amplifier, then they'll kind of put the Q point somewhere in the approximate, area where it's approximately linear. So any JFET MOSFET amplifier is going to be, 2, 5, maybe 10 small, because as the Q point moves back and forth, then we don't want to have a lot of distortion because it's inherently nonlinear. You don't have this problem with the BJT. Okay. All right. So to plot this out, I just used these parameters, use this equation. Okay. Right. So I would have used 12 milliamps there. VGS, okay, so VGS, then I started at 0, 1, 2, 3. And the more points you do, the better. Okay? But that's I found is sufficient. And the VGS off is the -7. So just keep changing that number, okay? And then you can fill these in, boom, and then you can plot that curve. Okay? Okay, so that's the end for this video. I'm going to then thank you all for watching, and we'll continue on in the next video very shortly. Thank you. Have a good day. God bless. Bye.